After defining the Laplacian matrix, let's see what its eigenvalues and eigenvectors mean. We'll start with an interesting fact that for a symmetric matrix M, its second smallest eigenvalue, lambda 2 here, is actually equal to the solution of this optimization problem, where X is a vector and M is a symmetric matrix. And you want to change X to minimize these objective function. And this objective function is basically X transpose times M times X over X transpose times X. And more interestingly, the optimal X to minimize this objective function is the corresponding eigenvector for this lambda 2. So what is the meaning of minimizing X transpose times the Laplacian matrix L times X on the graph G, where this L here actually corresponds to the matrix M here. So we can see that this X transpose times L times X is actually equal to a double sum over Lij times Xi times Xj. And since this Laplacian matrix is equal to the degree matrix minus the adjacency matrix, so B minus A, therefore this Lij is equal to Dij minus Aij. And if we split this into two terms, we can know that it's actually equal to here, where the first term is a sum over Dii times Xi squared. And this is because the degree matrix is diagonal matrix. So it only has non-zero entries in the diagonal. For the other entries, they're all zero. And the second term will be a sum over 2 times Xi Xj. So this is straightforward. Basically, this pair Ij indexes each edge in the graph. And this E is just the set of edges in the graph. So until now, you may have noticed that this node I in the graph, for each of them, it actually has a degree D. Therefore, the value Xi squared needs to be sum of D times here. But each edge, Ij has 2 endpoints, right? So we need both Xi squared and Xj squared. So basically, here, this large term will be split into Xi squared and Xj squared inside this sum. And by completing the square, we will have that this whole objective function X transpose L times X is actually equal to the sum over Xi minus Xj square, and we sum over all the edges. And this objective function basically says that if there's an edge between node I and node J, then we want to minimize its distance. Basically, Xi is the label of node I and Xj is the label of node J. So we will like to minimize the distance of their labels. So what else do we know about X besides what we have talked before? Remember that this X, the optimal X, is actually the eigenvector corresponding to the second smallest eigenvalue, right? So since it's a eigenvector, it has to be a unit vector. Therefore, if you take this vector and you take the square of its entry and you sum them up, it will be equal to 1. And also, since it's a eigenvector corresponds to the second smallest eigenvalue, then it has to be orthogonal to the first eigenvector. And we already know that it's for any Laplacian matrix, its first eigenvector will be a vector of all ones. And just to remind you, its first eigenvalue will be 0. So therefore, we have that the sum of xi for any x, any vector x would be 0. And remember that we say that we try to minimize this objective function, and the answer of this minimization is the second smallest eigenvalue lambda2. And the intuition of lambda2 and the objective function is that we want to assign values xi to node I such that the connected nodes have similar values, right? And we basically that we have said before, we want the xi and xj to subtract each other. So if we want to minimize that, and if there is an edge between I and j, we want that the difference between the labels to be as small as possible. And another interesting fact is that because of this node fact about the sum of square of xi is equal to 1 and the sum of x is equal to 0, the result of this solution is actually it tends to be a balanced solution. Why? This is because let's say that we have some of the nodes assigned to one group. So basically these xi will be smaller than 0. Then it has to be some other nodes that are larger than 0 in the labels. Otherwise, the sum of the labels would not be equal to 0, right? And after we do this, we can use this x as a label, and we can decide the final partition. So now let's go back to the problem of finding the optimal cut. We can express any partition A and B as a vector yi, where this yi will be equal to positive 1 if the node I is in group 1, and this yi will be equal to -1 if node I is in group B. So we can minimize the cut of this partition by just finding a combination vector y that minimizes the following objective function. So the following objective function basically is just we sum over all the edges, and inside this sum is just a difference between yi and yj, and we take the square. So basically it's the difference of their labels, and we take the square. And of course, since this y here is a discrete value, it can be equal to either +1 or -1. Therefore, it's actually very difficult to solve it exactly. So let's relax y such that we can allow it to take any real value as opposed to only discrete values. Then the problem will become something like this. We have still the same objective function. The only difference is that we now allow y to be a real vector. So each entry of the vector y can be a real value. And we have talked about this before. This equation is actually equal to y transpose times L, which is the Laplacian matrix, times y. Now this is actually exactly the same as our previous objective function. Remember that since the optimal solution, the x is actually a unit vector, therefore the x transpose times x is actually equal to 1. Therefore, the denominator here can be canceled out. So here we have that the minimum value of this objective function fy is given by the second smallest eigenvalue, lambda2, of this Laplacian matrix L. And the optimal solution for y is actually given by the corresponding eigenvectors x. And we usually refer to these eigenvector x as the theta vector.